Hello everyone, so this is just going to be a very quick run through of the practice problems that I gave out in class from the energy problem solving worksheet number 1. As you can see, I've got the first problem pulled up here, so here we go. A 5.4 times 10 to the negative 7 kilogram flea pushes off a surface by extending its rear legs a distance of slightly more than 2 millimeters, consequently jumping to a height of 40 centimeters. What physical quantities can you determine using this information? Make a list and determine 3 of them. So, the situation that we have is this flea, however you draw flea, that starts off with its legs compressed. He extends his legs and then jumps up 40 centimeters in the air. Okay, so this is part 1, part 2, and part 3. Since we are doing energy, obviously, let's just label this is the floor. Okay, we will make this our 0 reference point. And this is 40 centimeters, otherwise known as 0.4 meters. And this distance here is going to be 2 millimeters, or 0.002 meters, just for later reference. All right, so what we can do is we know the only information we know is that it jumps 40 centimeters or 0.4 meters, and he extends his legs 0.02 meters, and we know his mass of 5.4 times 10 to the negative 7 kilograms. So let's start by drawing a bar chart for the two scenarios, right? So the two parts from here to here and from here to here. So we start with the first one, which will include the flea, and we can include the earth in the system too, if you really want. Then what we've got is we have the flea starting off with effectively no energy, so no UG, no K, and ending up, if you want to be very nitpicky, you can talk about the very little bit of gravitational potential energy he has by pushing himself up 2 millimeters. I'm going to choose to ignore it because 2 millimeters is not very much and he doesn't have a very big mass. So his gravitational potential energy by going up 2 millimeters is not going to be huge. So I'm just going to say that he ends up, when he pushes off, he ends up with some velocity here. So he ends up with some kinetic energy and no gravitational potential energy. Let's move this over. So kinetic, no gravitational yet. So this is from part 1 to part 2. Now, to get this kinetic energy, he has to have done some work, right? Or rather, something has to have done some work. He is the system, so he can't do work on himself. So the work is actually done by the floor, pushing up on him. All right, so that's from part 1 to part 2. Then I'll sort of draw the second part here, all right, as if it was sort of continuing, right? Now, from part 2 to part 3, there's no work done because in this part we will include, again, the flea and the earth in the system. And he ends up with that kinetic energy turning into gravitational potential energy. By the way, you should draw 2 separate diagrams, right? One will just be this, and the other will be this. 2 separate bar charts, I mean. So, no work, all that kinetic energy is now turned to gravitational potential energy at part 3. Now, we know, we can calculate how much gravitational potential energy he has here, right? So we've got K is equal to UG, K initial is equal to UG final, right? And we know that K is 1/2 mv squared. We know that μg is mgh. So we can just solve for some unknown values, right? So one of the unknown values we can find is the velocity, right? Velocity of jump. Okay. In addition, we can actually solve for K or U, G, as the case may be. Once we find the velocity, we can go even further back and calculate the amount of work, because from this equation, or from this bar chart, we end up with work is equal to the amount of kinetic energy. Work is force times distance, which I'll write as d, and kinetic energy is again 1/2 mv squared. I don't know what I'm writing there. So we know what this is from over here. We know the distance, right? This is the 0.002 meters. That's how far he's pushing himself. And we can find this force, right? So we can find the work, which actually happens to be equal to these two. We can also find the force that the flea exerts, or rather the floor exerts on the flea as he's pushing himself up. So those are all the things that we can find here using these equations. I'm not going to do it. I will let you do that yourself to find the actual numbers. And anyway, the problem only says to determine 3 of them, so we could determine kind of any one of these. All right, moving on. Friction-based brakes are used to slow down a roller coaster. The coaster is moving at 20 meters per second and has a mass of 1,000 kilograms when fully loaded with people. If the coaster comes to a stop in about 10 meters, what was the force of the brakes on the coaster due to friction? And draw a picture, identify the initial and final states, and specify reference level you are using. So here we're assuming that it is on a flat surface, and the roller coaster, whatever, people, has some initial velocity of 20 meters per second. And at some point, 10 meters later, comes to a stop. All right. So, if we, again, use the energy bar chart to take a look at this, what we have is a situation where if we take the, that was weird, if we take the cart to be the system, the cart has no gravitational potential energy because he's not moving up or down. We'll take our 0p to be the tracks, right? Even if there's no gravitational potential energy, you should still define the 0p so that you know that there is in fact none. And if we look at the kinetic energy, he's got some kinetic energy. In the end, since the tracks are not in the system, right, there's no kinetic energy and there's no gravitational potential energy. So that means that the tracks will have had to exert this, friction force on our car, on our roller coaster car, the entire way. You can either remember that since the car is moving right, but the force is left, then it's negative work, right? It's taking energy away. Or you can realize that from the bar chart, if you have kinetic and then have nothing, then there has to have been some negative work of equal amount done on the system to eliminate the energy from before. So from this equation, we end up with K initial plus work is equal to 0, but since this is negative work, I'm actually going to do negative, right? And that means that if we simplify, K initial is equal to the work done, and from here we can say that, I'll write this up here, K is 1/2 mv squared is equal to F times distance. Now this force is the force that did the work, namely the force of the track, right, on the car, which is this friction force. So this is what we're solving for here. So if you want to rearrange it, force is equal to mv squared over 2d, right? And then that will be your friction force that you're trying to solve for. All right, and you can plug in those numbers and do that yourself. Next up. Roller coaster car drops a maximum vertical distance of 35.4 meters. Determine the maximum speed of the car at the bottom of the drop. Describe any assumptions. And will a car twice the mass have more or less speed at the bottom? Explain. So here's our picture. We know that this hill is 35.4 meters. We have a car, roller coaster, again, that drops this 35.4 meters down to the bottom here. Okay, and we will call this our 0 reference point, the point where the cart is at the bottom. So taking our system to be the Earth and the cart, all right, I chose the Earth so that I can put gravitational potential energy in the system. You'll notice mass is not given in the problem, I'm not going to worry about that. Oftentimes when a variable isn't given in a problem, there's a chance that it might cancel out later. So let's start doing the work and see what happens. So we've got a much nicer bar chart than before. UG initial, K initial, work. All right. So we start off with, okay, so we start off, I'm assuming we are only starting with gravitational potential energy, which means that I'm assuming that there is no velocity up at the top here, right? It is starting from effectively a standstill right before it comes down. That's a pretty big assumption, all right? Then ends up at the bottom with all kinetic energy, no gravitational potential energy. I'm assuming in this also, so assumptions. All right, I'm assuming that V initial is equal to 0, so that there's no kinetic energy. I'm assuming that there is no friction, okay? Because if there were friction, then there would be work being done on our system as it comes down, and this would not equal this. So, but we don't know what the friction force is here, so no friction, therefore work is equal to 0. And that's pretty much it. From here we can, again, use our conservation equation to say that UG initial is equal to K final, which means that MGH is equal to 1/2 mv squared. And you'll notice this m, right, is the mass of the cart, so it actually gets canceled out, like I said. So you've got GH is equal to 1/2 v squared. Solving for v, you get the square root, v is equal to the square root of 2gh. That'll give you your final velocity at the bottom. So that will do that. That's this equation right here, plugging in for g and the height of 35.4 meters. And also, if you notice, right, will a car twice the mass have more or less speed? It will not, okay? Because in solving this problem, assuming all the energy is converted from gravitational to kinetic, the mass actually cancels out in the equation, resulting in no mass having no effect on our problem. So the answer, I guess, is it will be the same at the bottom because the mass is canceled out. All right, moving on. Create a problem where the following is the solution. Draw a picture of the process, where the initial and final states. What is the ZRP you're using? All right, so this is called an equation jeopardy problem. Obviously, there's many different answers to what this could be. I would try to keep it realistic just because that's something that I do. So you'll notice here there is a unit effective. So what we do for a problem like this is we will look at the units and see what type of variable it is, what physical quantity it could be based on the units, and then we'll construct an equation from there. So we've got 1/2, and if you're quick, you can already see where this is going. 50 is m, right? 50 kilograms. Kilogram is unit of mass. 8 meters per second squared. This is obviously v squared. So this is our kinetic energy. Initial must be, all right? Plus 50 kilograms times 9.8 times 20 meters. So this could be a gravitational potential energy, right? 9.8 being g, this being the height, this being the mass, right? So again, 50 kilograms on all sides, plus mgh is equal to 1/2, again, that same m, and then v, what we're assuming is this v final squared, right? So this is the unknown value. So this is any problem that involves something with some kinetic energy and some gravitational potential energy and ending up with just kinetic energy. So obviously, whatever this thing is, I guess it's falling, right? And it's ending up at the 0 reference point at the bottom. So it could be like 50 kilograms. That's about the mass of a person. That'll be at a small person, about 120 pounds or so. So this could be someone, I don't know, jumping off of something and falling 20 meters, or moving at 8 meters per second while after falling 20 meters, or before falling 20 meters, whatever. There's many different answers to the problem. I'll let you pick your favorite. As long as it has some initial kinetic energy, some initial gravitational potential energy, and some final kinetic energy only. So it must end up wherever it is. It has to fall 20 meters and be at the zero reference point at the end. Now you might think to yourself, but if it's at the zero reference point, shouldn't the mg be zero? And we're looking really just the split second before it hits the ground. So that at the end here, it's got some final velocity right before it hits the ground and comes to a screeching halt. That is kind of the situation we're looking at. Last one. As a traffic cop investigating a car accident, you want to determine how fast a car was moving before its driver began to brake. While braking, the car's skid marks that are 70 meters long, the car left skid marks that are 70 meters long. According to the police report, the mass of that particular model of car is 1,600 kilograms and has a coefficient of kinetic friction between the tires and the road of 0.2. Was the car traveling faster than 40 miles per hour? Speed limit. Determine the car's initial speed. What are your assumptions? So, we've got some car moving at some initial velocity. Alright, and they're asking, is it 40 miles per hour, which we are going to have to convert to meters per second. I'll let you figure out how to do that. Just use Google if you can't think of any. We know it has a mass of 1,600 kilograms, and we know that when it's slammed on the brakes, it's skid for 70 meters. Right, so these are the skid marks here before it stopped. Over here, stop. Probably in some sort of fiery mess. All right. So the big question is, was it traveling this fast when it hit the brakes? And we know that mu kinetic in this case is going to be 0.2, right? The kinetic friction force. So the coefficient of kinetic friction, excuse me. So I'm going to draw a bar chart for the situation where the system is our car. All right. So it's gross. That's pretty. There we go. So just to be brief, I'm not going to include gravitation potential energy in this just because there's not any, it's just sliding. We know that it starts off with some kinetic energy. We know it ends up with nothing. So like before, it must mean that there must have been some work done by this coefficient of friction, right? The friction force from the road on the tires as it's skidding to a stop. So our equation is going to be kinetic initial minus work is equal to 0, which again, solving, we get kinetic energy is equal to work. These equations are, of course, 1/2 mv squared is equal to force times distance. Now, this force here is the friction force. If you recall, force friction kinetic, right, is equal to mu k times the normal force, or F normal, however your teacher writes it. In this case, because the object is on the ground, right, here's our force diagram for the object. This is force Earth on car. This is the normal force. Because it is flat on a flat surface, this force that Earth exerts on it is equal to the normal force. So we can use that to solve this, call this mg, and I'm going to take this and plug this back in here. So we've got 1/2 mv squared is equal to mu k mg times the distance. M's cancel out, and we can solve for v. So our v is going to be equal to the square root of 2 mu k GD. And plug in all those numbers. Now, again, you are going to have to convert this to meters per second because this solution is going to be in meters per second. So you will have to figure out from that if this equation, or if the solution to this is, greater than, less than, or equal to 40 miles per hour, whatever that is in meters per second. All right, there you go. Short, sweet, and to the point. And good luck. See you next time.